Alright, so continuing on with Chapter 7, we're looking at 7.4, and this is the first of two videos we'll do in 7.4. And with this one we're talking about calculating the length of curves. Now you can think very much like the length of curves being the same way we found the arc length with a circle, because they're very, very similar in what you're finding. Now they're not very similar in what you're actually doing though. So let's look at what we've got. Alright, so if we wanted to approximate the length of a curve over a short distance, we could measure a straight line. And this ds, the small length of a straight line, could be broken into dy and dx. A vertical component and a horizontal component. Now by the Pythagorean theorem we know that ds squared is going to equal dx squared plus dy squared. So therefore this ds will be the square root of dx squared plus dy squared. Now we could go ahead and do some algebra on this, and we could integrate both. And if we integrate over here, then we're going to get just s. If we integrate over here, well, we're not actually going to integrate there. We're going to do some math here, and we're going to multiply by dx over dx, because we need to get the dx out from under the radical. So if we multiply by dx squared over dx squared, we can take the bottom dx squared and distribute it through with what we've got here. Let me show you a little different here, because that jump right there doesn't exactly give it what you need here to see this, I think. So s is equal to the integral of the square root. And what we're doing is we're multiplying by dx squared over dx squared times what we already have here. Dx squared plus dy squared. Now, we're only dealing with the bottom part. We're going to take this bottom part, which we could think of as 1 over dx squared, and multiplying it times both parts in here. This dx squared we're just going to take to the very end. Or you can leave it out front. It doesn't, in front, inside, it doesn't matter, because we're going to end up pulling it outside of the square root in just a second anyway. But that's where we get, this is the intermediate step to what we get to here. So the dx squared on the bottom has been distributed through with what we had here. So dx squared over dx squared is going to give us 1. And dy squared over dx squared is the same thing as just the square of dy dx. So the length of this curve right here is the integral of the square root of 1 plus dy squared dx squared. And then this dx squared right here, we just went ahead and took the square root, so it pops out of the square root, because the square root of dx squared is just dx. That's where just the dx comes from. And then that leads us to this equation. The length of the curve in the Cartesian plane, this doesn't apply if we're talking about polar or anything like that. That's completely different. We'll talk about that later. But the length is the integral from a to b, the beginning value for x, and the ending value of x that we're measuring from and to, of the square root of 1 plus dy dx quantity squared with respect to x. So we're integrating from a to b of the square root of 1 plus dy dx quantity squared with respect to x. That is how we find the length of the curve in Cartesian. Alright, so for example, let's go ahead and find the length of this curve right here from 0 to 3. The function is negative x squared plus 9. So dy dx is negative 2x. So we have the length of this thing, and guys, these are actually really easy. Just remember this equation, and all you have to do is plug in the dy dx. Normally, if you actually have to find the length at all, you're going to have a calculator problem, so that you can do this as a calculator unless it's something easy that you can deal with. But with the square root, it kind of throws a kink in there, so it's not always easy. But anyway, it's going to be either a calculator problem or it's going to be one that they ask you just to set up. In other words, you would find the dy dx, you would plug it in, you'd find the upper and lower bounds, you'd put it all in place, and that's where you'd stop. You wouldn't actually have to calculate it. Now in this case, we're actually going to calculate, so we're going to put the dy dx in right there. So we've got the integral from 0 to 3 of the square root of 1 plus negative 2x, the derivative, dy dx, quantity squared, dx. Simplify that. Squaring 2x, negative 2x, you're going to get 4x squared. So you end up with the square root of 1 plus 4x squared. And since this doesn't fit any formula, we end up having to, even with a very easy example here, that's where we'd end up having to do either a calculator or an approximation or something like that. So when you put that in the TI-89, you're going to get the natural log of the square root of 37 plus 6 over 4 plus 3 square roots of 37 over 2. Nice and pretty, isn't it? But that's an approximation of 9.747. Remember, when you get that, when you need to get an approximation and it keeps giving you that crap, this kind of crap right here, remember all you're doing is diamond and then enter the equals. And that will give you an approximation. Now, you can also go into mode and set it to where it's going to give you an approximation each time. Now, a straight line going from 9 to here, or from 0 to 3, we could actually find out what that length would be by 9 squared plus 3 squared equals c squared. That gives us 81 plus 9, or 90, and the square root of 90 is 9.49. So this one should be shorter than this curve right here, so we're making it, you know, this answer that we come up with makes sense. Now, you can also let the calculator find the derivative too, even though with this case you really wouldn't have to. But you could actually put that in and store it as your y value, and then put this into the calculator. But see, that kind of defeats the whole purpose of you being ready and prepared to set the thing up. They would not give you credit if they gave you the function y and you just said the square root, integral of the square root of 1 plus dy dx squared dx. You'd actually have to put in the derivative and solve it. So calculator wise, this would work. I'm not a big fan of getting in the habit of doing it that way. So here all you're doing is you're saying you're taking the derivative of y with respect to x. You could also, if you put this in and was graphing it, you could also do that as d of y1 comma x, and you can also do that with the 84. Now, very important, if you ever store something as a variable like that, you've got to delete the variable when you're done. Otherwise, it's always going to plug in that thing for anywhere you've got a y. So you've got to be careful and do F4, 4, y, and enter. You can go through those steps with an 89 and you can see what it's going to do. There is no way that I know of that you can just delete a value. Plus the fact you can't store it as y with an 89 anyway. or 84. Yeah, you actually could. And it's going to leave that value until you store it as something else, but it won't mess with the graphing. This one may mess with the graphing. All right, so for example, if we have x squared plus y squared equals 1, and we want to find the length of this arc right here. Now, guys, there's a much easier way of doing this. Just understand, we're just verifying that it does give you the correct answer. This is nothing more than half a unit circle. So what's the length of this? The length of this is going to be pi. So if we solve the equation of this thing for y, we get y equals the square root of 1 minus x squared. Now, that's true because this is only the top. If it was the whole circle, remember it would be plus or minus. But since we're only dealing with y values that are positive here, we only have the plus square root. So the length of this is integral from -1 to 1 of the square root of 1 plus dy dx quantity squared dx. And when you plug the derivative of this thing right here in there, you're going to get 3.1415926,536, which is, of course, pi. And that's exactly what we're expecting for the length of the arc of a semicircle, or the circumference of half a circle with a radius of 1. All right, now if you have an equation that's easier to solve for x than it is for y, the length of the curve can be found the same way. You're just going to flip things. You're going to do a dy instead of a dx. And you're going to take the derivative of x with respect to y, not the other way around. Yeah, I don't like this. Hold on. Let me show you without doing that stuff. All right, so we know we've got x equals y squared. Well, the length we've talked about is going from a to b of the square root of 1 plus dy dx quantity squared dx. All right, now the thing is, you can change every variable in here to the other one and it still works. So you can also, now these are a and b in terms of x. Well, you can also do those a and b, the lower bound and upper bound, in terms of y. And everything is going to change. Plus dx dy. Now that's something that we have not seen or really talked about yet. Don't get confused though. It's the same thing. It's the derivative of the function x with respect to y. Well, here we have the derivative, the function x in terms of y, and then, of course, dy out here. So if we were going to do this and set this thing up, we're integrating. So in this case, we're going to integrate. Well, let me move over here and change colors, just so we know it's separate from what we already talked about. So this length of the blue line is going to be the integral from y value to y value, 0 to 3, of the square root of 1 plus, now what is the derivative of x with respect to y? Well, dx dy is just going to be 2y. So I'm treating my y like my x and my x like my y. So the same way I did before, where we did the derivative, we were taking the derivative with respect to x, so we had to put the dy dx conversion factor out there for implicit. We don't have that this time because we're taking our derivative with respect to y. So we have plus 2y quantity squared and then dy. And you can put that in your calculator. And guys, you can put x in here and here in your calculator, and it's still going to calculate it the exact same way. And you still end up getting about the same thing. Well, nope, sorry, exactly the same thing. Because it's the exact same curve, it's just turned sideways now. It's actually the inverse of what we were dealing with just a second ago. Remember, this would be y equals the square root of x. So it would be the inverse of what we dealt with just a second ago. All right, anytime you store for an x or a y, don't forget you have to clear those when you're done. So you can do F4, 4, x comma y, and enter. That means it'll clear both of those, and then enter.